these 5 bands. You then need to have coherent receivers. It means you need to have sophisticated DSP solutions that can support the transmission across all these 5 bands. And then you need to have tunable laters that you can have like bandwidth variable transceiver that can be tuned anywhere across this band. You then, if you want to go longer distances, you need amplifiers. So the amplifier technologies are required that you can go for long distances without any regeneration, and not only in C plus L band, but in all these 5 bands. So there are different technologies to realize that: doped fiber amplifiers, Raman amplifiers, semiconductor optical amplifiers. All of them together can make an optical line system possible. However, if you want to go beyond that and create a mesh network, which is required to sustain the current internet operation, you need to go to develop switches that supports add and drop capability. You can add traffic whenever you want and wherever you want, and you can drop it. And you can make what is called transparent optical network a reality. And that means you need to develop all these pieces together. So back in 4 or 5 years ago, there was not many research like on these topics, and that was the moment that one was born. So why not creating a training network that allows training several scientists, develop expertise on designing these kind of networks, so they can later on contribute to the European economy. They can also contribute to this kind of technology and make it a reality. And back then, several research institutions across Europe, they joined forces to realize this project, and that's when WAN was born. WAN is a doctoral level training network funded by the European Commission under H2020 Marie Skłodowska-Curie ICANN action. The core idea of WAN is to train 14 early stage researchers in this unexploited area of wideband optical networks. So that was the case like 4 years ago when the idea of creating this project has started. And these could happen by joint forcing several 14 highly qualified academic partners and industries across Europe to address different perspective of this networking paradigm, from the devices to create transmission lines to the networking switches or drop multiplexers to create the mesh network reality, and then also the software side, like creating algorithms and management and control plane to realize these kind of wideband optical networks. And the key and vision driver of WAN was really a challenging interaction between industry and academia partners to train these ESR with the required technical and transversal skills they need to contribute to the European society. You can do a PhD with using different funds, using different grants, but one of the key idea behind these ITN proposals or ITN project is to create a new generation of scientists that they care about other aspects, and they have like different kind of skills that is not easily achievable through a normal PhD program. And this happens by having secondments between industries, by having intersectoral secondments, international secondments, and by exposing these ESRs into different positions and situations. So they gained experiences, they can have visibility in the community, and they can make connections. At the end of the day, in order to be a successful scientist and contribute to the matters that are really important for the society, you don't need to only develop some scientific skills. You need to be able to communicate it to the public. You need to be able to consider impact for your research, like sustainable impact. For instance, now global warming is a real challenge, so you need to think about how to incorporate that and how the technology that you develop contributes to the for instance, Green Deal. And these are the matters that are important in these kind of projects. And it's not only about the science, it's about other aspects of science, like make an impactful contribution, particularly for the European society, for the European economy, by training these well-qualified scientists in these projects. And that was like how one was born, and one was born with the effort from multiple partners across Europe, from Portugal, from UK, Denmark, Germany, Belgium, Italy, France, Netherlands. All these partners, they joined forces to create this vibrant ecosystem. Now is running for a few years already, and the ESRs have already gained quite a lot of experiences and were exposed to different situations. Some of them currently in visiting sites, like as an external researcher or as in their secondments, which give them not only another flavor, another view of their technical side, but also from different cultures across Europe. So this is also another important aspect, that you can understand how different cultures can interact with each other. And this is usually very important because at the end of the day, as I mentioned earlier, it's not only about having paper submitted, it's not only about writing a thesis, it's about to learn how to live a life like a scientist, and how to care about the what is important in the society. And that means you need to understand what each culture cares about. And that way only you can be a different person or a different kind of scientist, that the matters of the humanity, which is also important for IEEE, can be taken into account. And during the execution of the project, several ESRs started to get hired, and eventually just 2 weeks ago it was completed, because a couple of the ESRs were not really on board at the beginning. And what you see here was also mentioned by Matthias. These are the PhD students, that they all coming from different cultures, not only from Europe. We have the ESRs coming from Brazil, coming from Iran, from East Asia, come from London. They all work together, they get to know each other, and they create also a vibrant networking experience for their future, where they can also support each other in their career development towards the end of their professional career. And by that, I would like to also then close my talk. So these are the matters that are important for these kind of IT and training programs. And these are in line with what is also important in IEEE. So they would like you to enhance technology, not only for the sake of the technology and the benefit of corporations or conglomerate, that it's just the benefit of the few, not for the many. The idea is that to invent and to do innovation, but for the benefit of everybody in the society. I am also a very proud member of IEEE. I'm with IEEE for more than 12 years, and this is just like personal memory that I wanted to share with you. Back in my bachelor studies, when I was involved for more than 2 years in student activity for our student branch, we did quite a lot of outreach activity, quite a lot of events, and we even received the appreciation from IEEE Iran section back then. It was very valuable experience for me. I learned quite a lot of things that even now today, it helps me in my career development, in my personal life, in my professional life. So I would like to then thank Matthews for organizing this event. It was quite also a personal experience for me to be here and share these few insights that I learned over the years with you all. And by that, I would like to thank all of you, and thanks for attending this meeting. I don't hear you, Matthews. I think you're muted.
Oh, okay, sorry. Really nice presentation, I said. Really nice to see that you have like a very long experience with IEEE back 10 years ago, I think, 2012, right?
Yeah. So I'm a member for like 12 years.
Yeah, that's really nice.
Yeah.
I just want to check if there is any question from the audience. No questions so far, but I have one question, Benim. If you could guess when wideband optical networks will be implemented, do you think it's like a matter of 5, 10, 15 years? Or do you think, okay, we are doing the science, but I don't think that we'll go. And I want you to be very, very honest with your answer in saying, I don't think that maybe we're going that far with S, O band, but maybe, or sorry, O and E band, but maybe we in 10 years, we may have deployed like S, C, and L. What's your, if you could guess about it in 10 years, what do you think is the scenario?
I think some of them are already being enforced. L-band is in many networks are operational. So I mean, in my conversation with operators, there are already L-bands operational in many places, and they are actually looking for solutions to primarily implement these technology, for instance, in access metro network when they have really problems with sustaining with their environment to cope with the capacity growth. And for the other solution, at the end of the day, it's a matter of which one is the winning solution. So if we talk about the O band or E band, I don't have a educated guess to provide, but I think S, C, and L would be just viable in a very near-term solution because the requirement is there. They need the capacity to grow. So personally, I had my personal experience just a week ago. I got my new SIM card, and it's a 5G SIM card, and has 1.2 gigabit per second just downlink. And that's huge, and it's massive. I mean, if you want to have like millions of customers in a single city and has all of them 1.2 gigabit per second downlink, you really need to change the infrastructure to address that. So I think in 5 to 10 years, S and C and L will be deployed probably in the even metro network. They are already, of course, available in like submarine networks for like these point-to-point connections.
Okay, so good to know your opinion. So thank you, Bena. I'd like to move on to
Thank
the
you,
next.
Matteo. So it was really a nice experience, and I really hope that all of you enjoy this project. And never forget that it's not only about science, it's about the networking, it's about gaining personal experience, and you all have a joint lifetime experience together, and just try to enjoy it and try to learn as much as possible and create strong ties that in the future of your career and professional life helps you out. Thank you again. Have a very nice day.
Thank you, Ben. And let's move on to the next talk, which is from Azul. And the title of his talk is Cost-Effective Capacity Increase of Deployed Optical Networks to Support the Future Internet, the Multi-Band Approach. So the floor is yours.
Do you see my screen?
Yeah, I can see it very clearly.
Okay, first of all, I want to thank you that accepted my request. And also, I want to thank Benham for his really great presentation that I think it was really good before my presentation. So today I'm going to present my work, which is cost-effective capacity increase of deployed optical networks to support the future internet. In other words, the multi-band approach that Behnam explained with more details. So let's go to the introduction part. All of us know that the traffic of the network increasing, so the operators need to increase their working bandwidth that nowadays working in the C-band with 4.8 terahertz. So elastic optical networks plays an important role to increasing the capacity of networks and also traffic grooming, and simultaneously usually using power efficient transceivers that use less power consumptions and also cost-effective ones. So for this regarding, the latest implementation agreement is 400ZR, which defined as a power-efficient and cost-effective coherent interface that supports 400G in the symbol rate of about 60 gigabytes. So operators have two main options to increase the capacity of networks. The first one is going to the multi-band, such as L-band and S-band, enabling parallel with the C-band, and also make use of regenerator to increase the capacity of the already deployed light paths. So let's start from the down layer, which means physical layer. All of us know that a multi-band optical line system amplification is like this figure, and so all of these connected with the optical fibers, and all optical fibers, when light passes through these lines, has attenuations. So what happens if we consider each links in a network, we see that we can get the quality of transmission and light path by this formula that we see, and we have the which PASE is the noise of the power of the amplifiers, and also nonlinear power in the formula, which is the nonlinear power of the light propagation in the fiber, and also total quality of transmission, which means GSNR value, has been calculated by this formula. So for a single span, which means one amplifier and one 75 kilometers fiber, we have these values for the quality of transmission. That in S band, we see that the 4 dB poor quality of transmission we have in comparison to the other bands, C and L bands. So we have the values that in here, 30 dB for the L band, 29 dB for the C band, and about 25 dB for the S band. So each values in each frequency is is equal to the quality of transmission of a single span, which is contains 75 kilometers fiber and also one amplifier. So if we go upper layer, network layer, we use by means of GMPY, we can estimate the quality of transmission of optical light paths, and then abstract our network as a weighted graph of the quality of transmissions. And also in here, we investigated two network topologies, German and US net topology that we see in the left side. And two investigation we have done in here that I want to show the effects. The end-to-end capacity of links in the topology without signal regeneration and with signal regenerator in the S-band I investigated, because as you saw, the quality of transmission in the S-band was so poor in comparison to other ones too. So in here, we focused on the S-band and also K-shortest path algorithm, and also for each network and multiple n-1 shortest path rules computed. And also the transceivers that we used in our networks analysis is like that the supports 3 modulation formats with different chromatic dispersion tolerance and power consumption and required GSNR of each modulation format. So regenerator assignment that we have done in here is like that. If you consider node A as a ingress and node D as egress, which means input and output, source and target, our algorithm starts to continuously check the conditions of required GSNR with the GSNR of the modulation format and also chromatic dispersion. In here, we see that our algorithm see that, okay, in node C, after node C, the chromatic dispersion or required GSNR is exceeds the required value, so it needs to put a regenerator in node C. And again, from node C to D, it starts to calculate the GSNR and also chromatic dispersion. The one thing, important thing is that the same modulation format used for end-to-end connections, no change at the regenerator nodes, which means wavelength did not change. And also modulation format did not change. And with this methodology that we use, excuse me, we hesitate to implement unnecessary regenerators in our network. Instead of putting, for example, an extra regenerator in node B, in here our algorithm only use one regenerator to increase the capacity of the light path. So about the results, we have see that, okay, in the DT topology in the left side, the total capacity is 520 terabit per second without regenerator. And when we put regenerator in only S-band, we see that the capacity increased to 591 terabit per second. And also for the US net, from 545, it increased to 546 only in the S-band. And also in here, we see the other values with detail about the power consumption and the number of devices, transceivers that we use by adding the regenerator in the S-band, only S-band. And in here, in the downside, we see for the total networks, these values are for the total bands the sum of all bands. So about the conclusion, I have to say that BDM has proposed as a cost-effective strategy to increase the capacity of optical networks, as we saw in the S-band. And S-band showing the worst optical performance, the use of optical signal generator in the S-band is proposed in our work in here, that it was so really cost-effective based on the values and results that we have gotten. And also, however, the approach leads to an increase in the capex and energy consumption, a little bit increase. So therefore, we propose to deploy optical signal regenerator only for light passes that's showing worse performance in S-band than in the C-band. And also finally, this way we get a more balanced network infrastructure, which means we could balance the capacity of the and quality of transmission in the S-band with comparison to the other bands. So it makes easy for the controllers to control their networks. Finally, thanks for your listening, and also if you have questions, you can send email. And also finally, I want to thank from the one project that has funded us. Thank you.
So thank you for the nice presentation, Hasu. I just
you.
want to remind the audience that for questions, you can use the chat. We have like a dedicated Q&A session for the questions. So if you have questions, we will deal with them during the Q&A session. So you can address the questions to the speakers as well. So now we have, thank you very much, Hasu.
Thank you. I need to leave, excuse me, because I need to go to the conference.
But thank you very much for your availability to attend.
Thank you. See you. Goodbye.
See ya. And now we have a presentation from Trish Yaunyan-Kuif from Fraunhofer HHI. And the title of her presentation is Indium Phosphide Mach-Zehnder Modulator for Wideband Optical Communication.
Okay, thank you, Matthias. Can you hear me?
Yeah, I can hear you.
Then let me share my slides. Okay. Here. Okay. My topic today is about indium phosphide Mach-Zehnder modulator for broadband optical communication. So we are going to solve 3 questions today. The first one is what is broadband modulator, what is Mach-Zehnder modulator, and why we use indium phosphide. So in our data transmission, our electrical data signal would first be modulated to be optical signal and then transmitted by optical fiber. After all these sections, it finally reaches the receiver where it becomes electrical signal again. Modulator as a part of a transmitter is used to modulate electrical signal to optical signal. Well, usually we have 2 definitions for broadband modulator. The first one is EO bandwidth, which is the range of frequency of electrical signal, our data signal, the modulator can handle. The second definition is about the optical wavelength range the modulator can use. So in our one project, we focus on the second definition. And the research on modulator nowadays mainly on O and C band, which is around 1.3 micrometer and 1.55 micrometer. So there are several different ways to achieve this electro-optical modulation. For example, the direct laser modulator, electro-absorption modulator, optical phase modulator, and our focus today is about interference modulator. Well, Mach-Zehnder modulator is a typical interference modulator. So it uses the interference effect of 2 branches of light. So here is the output, the power of output light. So we can see that with different voltage applied on this Mach-Zehnder modulator, the intensity of output light would change. So we use this change in intensity to transmit our data. So here is a detailed structure of a Mach-Zehnder modulator. So the working principle is electro phase shift here and followed by the interference effect of 2 branches of light. So the light goes into MZM, split into 2 branches of light. We have a DC signal here to give a bias to this phase shift. So our data electrical signal would induce the phase shift on the on either branch of light, and then they combine, and finally we reach this output light. So in order to get a broadband modulator, all of these components must be broadband. So if we have only one Mach-Zehnder modulator, we can achieve the intensity modulation as I showed you before. But if we have two MZMs, we can achieve phase modulation. One MZM used as I signal, the other one used as Q signal. Well, if we have four MZMs, we can achieve this dual polarization IQ MZM, which means we can use both TE and TM lights. So we have several evaluation parameters to evaluate the performance of MZM. First, we have Vpi, the voltage that would induce the phase shift of pi. So it characterizes the power consumption of MZM, so it should be as small as possible. And the length of device, the loss of device, the EO bandwidth to transmit more data, the EO bandwidth should be as large as possible. Then we can get a very high speed of MZM and some other aspects. And but not a single parameter is enough to evaluate the performance MZM, but all of them together. So you will always say from a paper that the figure of merit would be the product of Vpi and L, or the multiplication of all these parameters. So we will also use this figure of merit to make the comparison of different material used to make this MZM. So indium phosphide, silicon, and lithium niobate are all materials can be used to make MZM, but they have their own pros and cons. For example, the silicon, which is most familiar to us, it has better coupling to the traditional silicon processing. And lithium niobate, it has a high electro-optical efficiency, but indium phosphide has its own very unique advantage, because indium phosphide is also the material for other active devices such as laser amplifiers, so which means it can integrate all these devices together. It has a better level of integration. And in terms of other aspects, it also has a short device length, small power consumption, small loss, and high speed. So which means it is compared to other materials, it is a very strong competitor for making this MZM. And our group is also working very hard to make a high speed, high capacity, small footprint in the phosphide-based MZM. So that's all I want to show you today. Thank you very much for listening.
So thank you, Trish. Very nice presentation, very clear. Just a reminder, if you have questions for Trish, you can send them in the chat. We move on to the next talk from Gabriele Di Rosa, which is entitled Techniques for Digitally Optimizing Next Generation Multiband Optical Communication Systems. And after his talk, we have a Q&A session, and then we can discuss a bit about the presentation from Trish and from Gabriele.
Hello, do you
Hi.
see my screen?
Yeah, we can see it.
Okay, very good. So thanks for the introduction and welcome to my presentation about the techniques for digitally optimizing next generation multiband systems. So let's start with a bit of background and discuss first capacity achieving multiband systems. So as we already said today, with the internet services which are becoming more and more demanding in terms of data, we need in the very short term to increase the information capacity of our network. And if we have a look at our classic theoretical formula of the Shannon capacity, we see that a way for which we can linearly scale the capacity limit is to just increase the transmission bandwidth. And if we look at the fiber optic attenuation low attenuation window we see that we have still a lot of bandwidth which can be used with the multiband approach compared to actual commercial solutions. But when we go back to our formula, we see that we have another term, which is the signal to noise ratio and describes the signal quality, which is also in there. And we have to understand what happens to it when we operate in a multiband scenario. In fact, when we answered this question, it turns out that the signal quality with the actual technology is not preserved constant in multiband. So while for current C+L band system, we have a very small excursion of the signal quality, so all the channels can give similar performance, the variation increases very much when we consider already only the additional S band. So we don't get now into the details, but there are many reasons for this behavior, such as performance of current devices, as well as channel characteristic over the multiband, and even network management strategies that have to be optimized. But the point for us is that this is something that has to be taken into account, and we want to understand how we can approach the maximum capacity on a channel with a variable signal quality over the wavelength. And a solution to achieve this is to modulate the transmitted information rates versus the local channel performance. So if we start with the classic approach, we have fixed modulation formats and error correction. So this is simple, but it's limited in the performance, since every channel, also the worst performing one, have to work, and we don't have much adaptivity with this setup. We can do a first step and improve the rate adaptivity by implementing different error correction code, so we can trade off net informations versus performance. But the main problem of this approach is that we cannot design any kind of code, and we have limited granularity in the rate adaptivity. So a solution that instead established itself in the last year is to keep a fixed FEC and instead shape the signal modulation in order to carry fractional amount of bits. So if we look at this short video, we start with a 64-gram constellation which carries 6 bits per symbol. But when we go to modulate the amplitude transmission probabilities, we see that we can get any value between 2 and 6 and adapt it to our channel performance. But this powerful technique doesn't come without some additional challenges when we want to fully optimize operation over rate adaptive multiband systems. So for example, we have to improve signal processing to consider the signal statistics. And I will go fast here, but I just wanted to show some results from my work, which focused on improving the blind decisions at the receiver to improve the final information rate with shaping systems. And the point is that it can be shown that when we consider with the equations here the signal and noise statistics, we can lead to an improvement in the signal processing. So if we look at the picture on the right, we see that we have the standard decision boundaries of the algorithms, which are the red ones, but we see that the optimized one in blue are very different from the standard one when we have a lot of noise and strong shaping, as in the picture on the top. Another step in this sense is to limit the signal values which are used for the analysis in order to improve the robustness of system, which can use very low pilot overhead and so carry more net information, and again exploiting the signal statistic work more reliably. So for example, in this figure we have that a signal sample is considered to update a filter only if it falls inside the green areas, since these give us more reliability on the accuracy of the decisions. In parallel, another thing that has to be understood is what are the requirements on the transceivers and if current devices can effectively operate in a multiband system in the short term. A problem, in fact, is that everything that I've shown until now, it's valid, and the equations work for additive white Gaussian noise channel. So both signal processing and FEC are based on an auxiliary AWGN channel, but in reality, transceiver impairments make the system deviate from this assumption. So if we look at the constellation after the receiver that is shown in this slide, we see that if it would be AWGN, it would be inside the green circle. So clearly it is not, but our DSP can adaptively recover the constellation and in the end gives us something that is Gaussian somehow. But the problem is that this comes with performance penalties. So we have to understand the amount of imbalance that it's introduced by the transceivers versus the wavelength. So we looked at this, we experimentally characterized for commercial devices, and we noticed that a critical point is that the imbalance grows versus the wavelength on the receiver side when we move outside the C-band. The transmitter, on the contrary, kept constant performance, and then we try to understand what is the impact of this finding on the final system performance. And if we reconnect this to our signal processing analysis, the point is that luckily we can compensate for the receiver at the start of the DSP chain, so we can get rid immediately of the impairment. On the contrary, transmitter imbalances are problematic since they can be corrected only at the end. But if we recall what we just saw in the previous slide, we saw that only the receiver had a clear degradation versus wavelength. So the final conclusion for our work is that we can work and we don't observe a clear penalty on the achievable information rates with these standard devices used in multiband, at least in these conditions. So let's come to the conclusions. In this very short presentation, I try to show you the challenges that arise when we increase the transmission bandwidth in terms of uneven system performance. And I showed you the main topic of my research work, which consists in developing and analyzing optimized digital signal processing schemes to cope with these additional challenges. Thank you for having followed and to the European Union for funding this project.
Thank you, Gabriele. Let me open. A second. Yeah, so we are open now for questions. See if there's any questions from the audience. No question in the chat, but I have two questions. One for Trish. So you showed like a comparison between these three technologies for modulators, right? Silicon photonics, indium phosphide, and lithium niobate. Could you comment on, for example, the costs of these three technologies? Because if you're thinking about deploying that in the field, replacing the transceivers, for example, the operators would be very concerned about the costs of these new technologies. Do you have an idea about that?
Thank you for your question, Matthias. So from my view, I think the silicon is the most cost-effective material to make MZM because we all know that most of the chips devices are made of silicon, but silicon is really a bad material for the laser and active devices. So if we talk about indium phosphide, if we talk about the integration, so indium phosphide must be a better choice. But yes, indium phosphide, like compared to silicon, indium phosphide costs more, but we already have very mature commercial modulator for indium phosphide. So I think in nowadays, indium phosphide is also a very cost-effective material. Yeah.
Okay, thank you. There is one question from the audience. Did you look as well? It's from Robert Emmerich. Did you look as well into the plasmonic modulators for multiband?
Yeah, I actually know very little about the plasmonic modulator, but I know there's some development in this plasmonic modulator. But what I'm studying now is mainly about indium phosphide, which can be integrated to other active devices. So about plasmonic modulator, I know very little. Sorry.
Okay. And there's another question for you, Trish. What about thin film lithium niobate modulators? I think I see that it became a popular research topic for high bandwidth device recently. That's a question from Gabriele.
Yeah, of course. Thin film lithium niobate modulator, it has all the advantages from legacy lithium niobate modulator, and also it has its own advantages, especially that thin film lithium niobate has a very small footprint compared to the legacy lithium niobate modulator, and it also therefore it has very small VPi times L. Well, I think I think recently it becomes a very popular research, and I can also see a very promising future for this type of material.
Okay, Trish, and I have one question now for Gabriele. So, do you think, I don't know, I just was wondering, do you think that, for example, when you have different amplitude imbalances and different phase imbalances, would that elevate the degree of complexity of your DSP, or that it's something that the DSP, it's like transparent to your DSP, it doesn't elevate if you have like very high IQ amplitude imbalances. What do you think about that? I think you're muted.
Yes, sorry, Matheus. I had lost connection. Can you tell me back?
Can you should I repeat the question?
Yes, thanks. I had very bad audio.
I asked you if you have like wavelength dependent amplitude and phase imbalance, for example, would that elevate the degree of complexity of your DSP? Do you think, for example, for a certain wavelengths that your DSP would require more processing, or your statistic-based techniques can deal with that without much change in terms of complexity of your DSP implementation?
On the transmitter side, yes, it would. So on the transmitter side, well, it depends on the nature of the imbalances. If well, first they will lead to performance penalties because they will stay uncompensated for the first DSP stages. So equalizers, phase recovery, and other algorithms would degrade the performance because they would see a lower effective signal quality. But apart from the additional penalty, which of course is unwanted, to compensate them, it depends on their nature. So if you have frequency independent imbalances, which it's the common thing, you would have not an increasing complexity. I would think short equalizers could be enough for it. But if you start to have frequency selective imbalances over multiband, then yes, your DSP should change, and you would need more expensive adaptive filters to compensate for it.
Okay, great. There's one more question. Actually, I think this is for Hasu. Maybe Rob, you can.
I'm happy to answer it, considering Russell's not
Oh,
here.
okay, good. That's really nice. Go ahead, Elliot.
Yeah. So yeah, the question was, are there a lot of comparisons for GSNR on the S-band for simulation versus experiment? So from the literature that I've read, there is I'd say a handful of simulations for the S-band. Of course, the work that Rasul has been doing has been calculating S-band capacities from a wider network point of view. But if we're talking more towards the physical layer, so at the moment, I'd say there's a disjoint between the S-band for experiments and simulations, because, for example, lots of people have been doing simulations for the S-band, but have not been properly considering, some of the effects that you need to consider in a wideband scenario. For example, input power optimization and the stimulated Raman scattering both need to be tackled very well to accurately predict the S-band. But in the same way, the transmission experiments that have been going on for the S-band haven't been paired with very thorough modeling, because I don't think at the moment, there isn't a lot of, let's say, laboratories that have the capacity to do wideband transmission and also the modeling capabilities. But the key point is,
from what I've seen in the literature, this is starting to become a little bit more commonplace, and I think we'll start to see some C+L+ S-band transmission experiments and modeling in the near future.
Okay, thank you for your availability in answering this question. So now you were the next, right? So the next topic
yes, that's right.
is from Elliot from Politecnico di Torino, and it is entitled Minimizing NLI Impact in Open and Disaggregated Optical Network Infrastructures. So
yeah, that's right. So I will just share. Give me 1 second.
no worries.
Okay, can you see my screen?
Yeah, we can see it.
Okay, so as Matthias introduced at the beginning, my name is Elliot London. I work at the Politecnico di Torino together with Rasul and Bruno. And I mostly focus upon the physical layer modeling and impairments within wideband and disaggregated optical networks. So the title of my talk is Minimizing the NLI Impact in Open and Disaggregated Optical Network Infrastructures. So within this presentation, I'm just going to give a sort of outline on the differences between disaggregated and wideband optical networks and why they are both very important things to consider when you want to do wideband modeling. For example, the disaggregated model ties in very well to when you have a wideband model. So just as a bit of background, of course, I assume everybody knows that we have extremely aggressive capacity and throughput demands that we're facing for optical networks and optical network infrastructure, both now and in the coming years. As Bernam mentioned, you have different 5G services, you have cloud services, virtual reality is starting to get quite popular, and of course you need like huge amounts of bandwidth. So that's exactly why we've decided to go for this wideband approach, because it's a great way to theoretically get extra capacity at no additional infrastructure costs. You don't have to install more fibers. Well, you have different components, which of course you have to pay for, but the physical fiber installment shouldn't be something that should be needed too much. And as Rasul mentioned, at the moment we're entering state-of-the-art standardized configs such as the 400G ZR+, and at the moment that standard just goes for the C-band. So, okay, what about disaggregated networks that I mentioned previously? So going hand in hand with this development towards wideband networks, networks also are requiring a greater degree of flexibility, because it's a really useful thing that you can use to help maintain network uptime when you have such a large amount of bandwidth demand and end user demands. So a disaggregated optical network, or partially disaggregated, which is what we generally consider these days, is if you consider, rather than having your optical network where you say, okay, I've got point A to point K, and you go all the way across the path, and you consider it as a point-to-point. For a disaggregated or partially disaggregated optical network, you wish to consider every single OLS within, for example, connection A to B and B to C, all independently. And you also must bear in mind that within these infrastructures, and this is something that's starting to become more common, in that you could have multiple different vendors operating on the same OLS, because you could have different wavelengths controlled in different ways, and there's no unified standard. And as C-bands are being upgraded to C+L+S and beyond networks, it's going to be, I think, uncommon to find networks that are completely managed and fully standardized by one vendor. So it's very, from my perspective, very important to make sure that you can model your network by considering each OLS independently. But of course, all these things that I've just mentioned give you some real difficulties for quality of transmission estimation. For example, the WDM grids that you're considering could be flexible. You could say, let's say you've got 64 channels on the C-band, each of 75 gigahertz spacing, but then, somebody wants a request on the L-band and they go, oh, okay, I know that the L-band doesn't work very well in this network. Therefore, I want to transmit some channels at 32 gigabaud, 50 gigahertz. So you need to be able to model all of these channels differently. You can have non-fixed transmission parameters in the same way you can have some people transmitting with 64 QAM, some people with QPSK, some people even with a CW for some random experiments that they're doing. And also, this is very critical, you can have light paths of unknown parameters or histories, where you would have different vendors in a network. They may not be willing to disclose confidential information about their transmissions to each other. So you could be asked to manage in a network multiple different channels that you really don't know much about. Of course, you can measure the symbol rates and the powers if you wanted, to do some in-depth analysis, but this is also just estimates, right? So it's not ideal. And if you imagine all of these above problems, you're going to have in the scenario where you have wideband as well, where the transmission impairment is a bit harder to model. So this, as you can tell, is a bit difficult. So how do we model this? So from our side in Polito, we use tools such as the split-step Fourier method and the open source GMPy library, which are two. I'd say the SSFM is a very widely used tool, is very accurate for modeling the physical layer, and there are many different libraries which you can use to do this in a quicker way, such as GMPy. And we do this using the generalized signal to noise ratio, which is the inverse sum of the nonlinear SNR, which is all the nonlinear impairments, and the optical SNR, which is all of the linear impairments, for example, the AC noise from the amplifiers, input and output connector losses, etc. So for disaggregation, we need spectral and spatial separability. So we need it so that every channel can be considered independently and every fiber span can be considered independently. So, okay, great. Why don't we just start from a disaggregated Gaussian noise model? The Gaussian noise model is used for, well, the basis for all modeling that is done for the physical layer and optical networks pretty much these days. But how do we do this? Because the SPM, which I'll speak about in a second, is not spatially separable, sorry for that error. So the nonlinear interference, the SNR-NL that I just mentioned, is composed of the SPM, self-phase modulation, which is the impact of the channel upon itself, and the cross-phase modulation, which is the impact of all other channels upon itself. So the XPM has no problems here because you can separate it per channel, you can separate it per span, but the SPM has a phase memory. So if you want to consider, fiber span after fiber span, it can be really difficult if you don't know anything about the light path. So we investigated the SPM and we found that it has an asymptote. And this is quite nice because it means that you can estimate the maximum amount of SPM that you're predicted to accrue within a system. And we use this for an accumulation model. And this means NLI can be disaggregated if you consider it from this approach. And I just show quickly two results that we have here, where if you consider the coherency of the SPM, the blue line is a full spectrum transmission, and the red line is the coherent SPM plus each of the individual pump and probes. And you see through these simulations, you get like a really high level of accuracy if you consider it within this way. But what about wideband networks? So in wideband networks, the stimulated Raman scattering must be considered. It causes significant power transfer between the bands. And of course, the NLI is dependent upon the power of the channels which you're transmitting. So this makes things very messy. It implies complex power assignment, modeling, and margins. However, we discovered that the interband NLI is negligible. So if you have the C-band, the NLI that you generate within the C-band mostly remains within the C-band, and the same for the L-band. So I know that this is quite a detailed plot, so I'll just explain it very quickly. So the two important ones here are the blue lines, which represent the L-band and the C-band being transmitted independently, and the dashed green lines, which is what happens when you just add the nonlinear interference, the NLI. And as you can see, the greatest difference only lies at the edges of the bands, and even then we're talking about 0.4, 0.5 dB. So yeah, as I said, the interband NLI seems to be quite negligible, and we're still doing some investigations on this for some future publications. So this has great implications for wideband transmission. It means that, as I mentioned before, arbitrary and even unknown spectral loads can easily be modeled because you can okay, you can see how the SPM is accumulating, and therefore you can work out how far away you must have had the SPM. This also implies, for example, seamless wideband upgrades, because as the interband and LI is very low, you have your C-band, add your L-band, and you only have a very small impairment on the currently transmitting C-band. And this also implies a greatly reduced computational complexity, because, for example, if you wanted to consider a really wideband case of, for example, 30 terahertz, doing a split-step Fourier method with even reasonable level of accuracy, this could take months. Whereas if you want to reduce it by not including the channels that don't include a large amount of NLI, this could take on the scale of days instead. So I would just like to finish by saying that combining with advances in hardware, software, and fabrication, which is the rest of one, from at least an NLI management standpoint, wideband transmission is much closer than we think and very feasible. And yes, so thank you very much for listening. That's the end of my presentation. Yeah, thanks again.
Thank you very much, Elliot. So if you guys have questions for Elliot, just type in the chat and he will answer it in the Q&A session. So now the presentation is from Pratim Hazarika. He is from Exeter University, and the title of his presentation is Raman Amplifiers Remote Band Optical Networks.
Thank you, Matthias, for this invitation. Can you see my screen?
Yeah, we can see it.
Okay. Thank you for giving me this opportunity. So my name is Pratim Hazarika, and I am from Exeter University under School of Engineering and Applied Sciences. So today I'll be talking mainly about amplifiers for multiband optical and specifically focusing on Raman amplifiers. So this is the motivation of my presentation today. So basically, as has been told by most of my colleagues, so why we are pushing this towards high bandwidth. So as we are, so you can see from this figure 1, the Cisco VNI report, and it shows that the demand of data has been increasing with each passing years. And at 30% computed growth rate, we can see that the number of hotspots has reached more than 600 millions across the different regions of the globe. And with this exponential growth of data consumptions, we need this technology for an upgradation. And basically, there can be 3 strategies. First can be utilization of the dark fiber, which already has been in the existential fiber networks. Also, we can use high capacity fibers such as multi-core and few modes, but this requires a complete upgradation in the entire networks. And third can be use of multiband transmission, which is the main agenda of this entire presentation, where you will be using the spectral bands apart from the conventional bands. And in this, we will be mainly focusing on this third strategy. So speaking of a multiband transmission, a typical multiband architecture can be segregated into 4 stages, where we have the transmitter stages, and we have the ad-hoc multiplexing using the ROADMs, and then the inline stages where you have different amplifiers for as an inline, and then we have the receiver stages. So we need these devices which can modulate, amplifies, and process these signals within this entire bandwidth. And today I'll be mainly focusing on the amplifiers part, which is the inline amplifiers for that can amplify signals in these unused spectral bands. So speaking of amplifiers, we can have basically 2 technologies that can be dope fiber amplifiers or other amplifiers based on nonlinearities. And on dope fiber amplifiers, as you can see from figure 3, we have different dope amplifiers for different bands, which can operate at different wavelengths, which can be pseudonium dope fiber amplifier for O band. We have bismuth dope for E band, and for thulium dope for S band, and for C and L band, we have traditional erbium dope fiber amplifier. And we combine all these amplifiers together, segregate the signal, amplify, and then again combine the signals. Also, there can be other amplification techniques which are not based on doping methodology, which can be fiber optic parametric amplifiers and semiconductor and Raman amplifiers. And till date, this has been the bandwidth that has been tested with different kinds of amplifiers. So I will be mainly focusing on Raman amplifiers. So before going on, how can Raman amplifier be used for ultra wideband systems? I want to show how Raman amplification takes place. So basically, Raman amplification is a process of annihilation where you pump at a high power laser diode, and then it excites to an higher energy states. But when we de-excites to the ground state, it shifts at a particular wavelength. So this wavelength shift has the same phase as that of the signal photon. So this photon will transfer this energy into the signal, and this is what is called the Raman process. And this difference in the energy between the vibrational state is released in forms of energy vibrations. And this Raman effect occurs at around 100 nanometer downshifted from the pump wavelength. So you can see from figure 5, when you have a pump at around 45, 50 nanometer, you can have some AAC spectrum around 1550 regions. So here, all the signals that will be lying within the 1550 regions will undergo transfer of energy from this AAC spectrum and will gain the energy, and the signal will correspondingly amplify. But as you can see from this spectrum, it is not at all flat. It is some kind of a triangular spectra. So what we do is we use multiple pumps, and then it causes an averaging effect, and we get somewhat kind of a flat spectra across the bandwidth. So which can be seen by the dotted magenta lines, where we have used like 5 pumps, and then it gives an spectra across a bandwidth of around 100 nanometers. And all the signals that will be lying within this magenta curve between this will undergo transfer of power and will go under amplification. Now, speaking of amplification type, Raman can be done in 2 different methodologies. So that can be distributed and discrete. So first, moving towards distributed, which can be further segregated into 2 sections. It can either be done in a backward pumping or in a forward pumping scenario. So in the backward pumping, what happens is, mainly first speaking about distributed, in distributed amplification, the SMF fiber can itself act as an amplifying medium. So the signals will undergo attenuation, but also amplification at the same time. And in the backward pumping, the pumps are at the backward stage. So the pump signal propagates in the direction which is opposite to that of the signal, as you can see by the arrows. So you pump from the backward direction and it will undergo amplification. While in the forward case, the pump and the signal propagates in the same direction. And you can see from this curve, the pulse propagation, we can see that the red line when we have no amplification. And in the case of backward pumping, it will undergo attenuation and then amplification. And at the edge output of the SMF fiber, you will have the same power as that of the input of the fiber. So this is methodology is known as distributed amplification. And while in the forward pumping, it will undergo amplification and then attenuation. And at the output of the fiber, you will have nearly the same power as that of the input. Unlike everything in life, we want to move forward, but generally in Raman, backward pumping is more preferred in distributed fashion. The details are like quite complex, and it requires a separate session to explain why backward pumping itself is better. Also, we can have a third architecture, which is known as bidirectional. So what we do is we do both backward and forward pumping, and in this case, we do a certain amount of pump through forward direction and certain amount of pump in the backward direction. And you will have a spectra, the signal propagation somewhat like this red curve, where you have amplification and then it goes down and then again it's amplified. And at the output of the fiber, you will have nearly the same power as that of the input. So the inline amplifier can compensate the losses in the SMF fiber section. Now moving on to discrete Raman amplifiers. So this is something which is similar to EDFAs based on LUM technologies, where we don't amplify in the SMF fiber, the transmission fiber, but we put a special nonlinear fiber after the transmission stage, and then we backward pump in the gain fiber so that the signal propagates in this direction and the pump propagates in the opposite direction, and there is a gain that occurs within this fiber. And you can see from figure, we have different spectrum, where WDM spectrum, and this undergoes gain within the short range of the gain fiber. So we typically keep 6-7 kilometers of fiber as the gain fiber, and we pump in this direction and prevent the pump from going to the SMF using an isolator, and the signal direction gets amplified in the gain fiber, and we get a corresponding output. Now, this gain fiber can be of different nonlinear fibers, which has low effective area. And some of this gain spectrum can be seen here of different fibers. These are like Corning-Raman fibers, dispersion compensation, and inverse dispersion fiber. So depending upon the application and the amount of gain required, we can choose different kinds of fibers that will be best suitable for us. So this is the general methodology of how Raman amplifier works. And as we move towards multi-band systems, there have been recent results shown from my colleagues and me, where we have different architectures to amplify 150 nanometer, which has been experimentally verified. So we can have different amplification techniques. We can't put all the pumps together at one and put one fiber for gain, but rather we have different architectures where we can amplify different bands of signals and then combine and proceed towards further transmission. So this can be different, such as split combine approach, where we split the signal of S-band into this part and amplify with the corresponding pumps from 1365 to 1425. And then we combine, and the corresponding C and L band can be amplified using this stage, single stage. And also there can be different kinds of architectures which based on hybrid, where we do distributed for the S-band signal within the SMF fiber, and then we separate out, and then we do discrete amplification for the CNL band, and then we combine and again further propagate. This is what we call it, mainly a hybrid architecture, combining both discrete and distributed. And also we can have dual stage architecture, where we put the S band in one stage and CNL band in one stage, and then we propagate for further transmission. So these are the different kinds of architectures, and well, results of it are in these two papers. And so with this, I'd like to end up the summary, and we believe that multiband is a very progressive technology, and in terms of moving towards such system, we require aggressive research, and in terms of network capacity, inline amplifiers, modulators, and switches. And speaking of amplifiers, Raman amplifier is a very promising candidate, and it can amplify more than, it has experimentally been showing that it has amplified more than 150 nanometers, and we are pushing it more towards 200 nanometers. And in the future, it can extend the optical window covering the entire spectral range. So thank you. Thank you for your attention. And I would like to thank all my collaborating partners, and especially WAND and the European Union for this project, and IEEE for giving this opportunity. Thank you so much.
Thank you very much, Prateen. So now we follow up with the presentation from Rafael, which is entitled Optical Wavelength Switching and its Role in the Move to Greener Networks. The floor is yours, Rafael.
Thank you, Mateus, for the introduction. So let me share my screen. Can everyone see the presentation mode or no, right? Stop it.
Yeah, I can see it.
Yeah, okay, cool. So good morning, everybody. Welcome to my talk. As Mateo introduced, I will be talking today about optical wavelength switching and its role that in the move to a more green optical network. The talk will be mainly divided in 5 parts. First, I'll talk briefly about the evolution of optical networks. Then I'll talk about what is optical wavelength switching, followed by a brief description of modern metro access networks. Then I'll show some results that validate our work and the role that optical switching plays in future and modern networks. And finally, I will conclude this talk. So as optical networks first arrived in our modern world, the first links were point-to-point links. It was basically you were connected from point A to point B with a fiber transmitting information and another one receiving information. And at each point, you have, for example, from transmitting from A to B, you had a conversion from the electrical domain. So you have bits, 1 and 0s, that you convert to the optical domain, light. And then on the way back to point B, where you are receiving the information, you have another conversion from light to bits again in the electrical domain, 1s and 0s that you have on your computer. As time passed and optical networks started gaining more more adapters in the network, you have more users coming in. So as you have more users, the point-to-point that we have before is not suitable anymore. Then we start moving to a ring topology, for example, that you have several nodes interconnected in a ring. That's basically what the name says. But in this ring, for example, if the user A wants to send data to the user, for example, in the C node, it will need to traverse the node at B. And during this conversion, when you get to the point B, there will be an optical to electrical conversion, and then another electrical to optical conversion to get to node C. What that means is that you have a power-hungry operation. You have super bulky switches that requires lots of cooling because it consumes lots of power and it gets really hot. And also, again, the network keeps evolving. So new standards come in. So you have now 100 gigabit Ethernet, now 400 gigabit Ethernet, and it will keep evolving. And that means that you need to spend money at each generation of electrical connections. But if you move to optical wavelength switching instead of the electrical one, we avoid first the power-hungry electrical optical conversion. So you save power, you have a more environmental friendly network. You have a transparency. The optical domain doesn't care if you're transmitting at the 100 gigabit Ethernet standard or 400 gigabit Ethernet standard. It's all light. We can process light. There are some restrictions, but usually we can process light independently. And it's also faster because when you get to the electronic switch, you have some, let's say, memories that gives some kind of random latency from one point to another. But in the optical domain, our latency we know beforehand because it's just the time that lights takes to propagate from one point to another. And it also supports pay-as-you-grow approach. So you don't need to buy a switch that has 40 or 400 ports or something like that. You buy a small device in these small networks, and then you keep buying more optical devices as you grow the network. And in modern method access networks, already talking about what we have in the world today of 5G and whatever will come after that. You have several nodes that, for example, from one data center, you are going from to a 5G antenna and the traffic keeps exploding. So this comes to the point of the one project. So we aim to support this traffic explosion by exploiting multiband. And these nodes, these modern networks, I have here some statistics that you can check. So you see that the distance between nodes is on average 1.6 kilometers. The node degree, that is the amount of nodes that each node is connected, is around 2. And the number of hops, that is the number of the number of nodes that each optical signal will traverse, it's on average 5 for these modern and future networks. And we already validate a multi-band approach by employing the O and the C band. More recently, there are several works that we are also export switching in other bands, but this is just a more general approach that we done recently, employing semiconductor optical amplifiers that we have. We can also amplify the light power at each switching node. And here's just the description of our setup. We had on total first 12 kilometers of fiber and then 25 kilometers of fiber in this distribution. So here basically the O band is traversing only 12 kilometers and the C band is traversing 12 plus 25 kilometers. And just showing that we can do that with some penalty, of course, because there's nothing free in the world, but the optical switching can still support traversing several nodes as the electronic switching also supports. So here we're just showing that we still have a good signal to noise ratio after traversing 3 nodes in the C and then in the O band. And also in the what matters is the bit error rate. We can see that the penalty is quite small if we cascade several nodes. So this is also a scalable solution for the future of these networks as the number of node servers keeps evolving. And just to conclude this brief talk, I just presented that optical switching is a cost-effective, future-proof solution for multi-band optical networks, and also we can avoid optical electrical conversion and robust cooling solutions. With that, we can reduce the power consumptions of these optical nodes, and we can, with this, probably move to a greener future in these optical networks. That is quite important for us and for the future generations that will come. Thank you. And if you have questions, drop in the chat that I will answer later. Bye.
So thank you, Rafael. Very interesting talk. I want to see if we have some questions from the audience for the last three speakers. I mean, Elliot, Rafael, and Pratim. No questions so far, but I have a few for you guys. The very first one is for Elliot. You mentioned that the operators are not willing to provide information from their systems, but I would like to, I don't know if you know it, but what kind of information, what kind of basic information can acquire from amplifiers and fibers that the vendors can provide it to you, and what kind of information you can estimate from your received signal? Do you know how you what kind of information you can receive it? You can estimate it from the receiver.
So yeah, so I said that vendors may not be willing to communicate with each other. This is something that I'm assuming will probably be the case. So it's sort of a worst case scenario. So the information that you require that's essential to modeling the NLI is you basically need the symbol rate of the signal that you're transmitting. You need the width of the WDM grid within which the channel is transmitting. You need to know what neighbors the channel has, at least within the local spectral region. And to a lesser extent, it's useful to know the modulation format. And of course, if we're talking about the fiber themselves, you really need to know the fiber dispersion. You need to know the physical parameters of the fiber, such as the gamma, and yeah, for example, maybe even the beta 3 in extremely wideband cases. So, for example, and of course, fundamentally, you need the channel power. So if you are working within an optical network, let's say you're within, it goes from A to K, something like this, and you're working at node C, and there's a vendor that isn't willing to share any of their information about the signal that they're transmitting to you. If you have a channel under test, and then you could have a channel that's transmitting that isn't your channel under test, you could work out roughly what the power might be by working out, comparing the spectral occupancy of the signal with other channels within the spectrum to work out if it has a similar baud rate. And then from this, you could work out, like, for example, power scaling. But this is all like, really unoptimal sort of estimations that you can do in a worst case scenario. So this is the whole point why I underlined why it's really important to be able to work with a disaggregated NLI model, because if you have a fully aggregated model, you just go, okay, I know nothing about this channel. Let's just say that we have the worst performance possible. But if you have a disaggregated model, you can attempt to put in some edge cases with these different channels that you have, and like limit the amount of impairment that you have from this channel. For example, in worst case scenario, you would know that the channel under transmission could be a Gaussian modulated symbol, because this could be the worst case. And you say, okay, forget it. I'm not going to try and work out what's going on with this signal. I'm just going to say that it's Gaussian modulated, which a disaggregated model allows you to do so, because you can vary all the different parameters of all the different channels that you have, rather than just saying, okay, whatever. Because another important point that there is within this sort of framework is the vendor could be transmitting this channel, but they could change it without much notice. So you could just be, okay, you could spend like a week trying to measure like subtly and secretly like what parameters are going on, just for like internal use, so for your own models. And then within like couple of days, it could change. So this is sort of why I highlight it's important to be able to measure every channel and every fiber span separately. I hope that answers your question.
Yeah, for sure, for sure. I would continue discussing about that, but we are
Yeah, sorry
out
if
of
I keep going over.
Yeah, and also I'd like to ask a question to Rafael and Pratim. Actually, it's something that you guys can discuss together, because both of you highlighted the fact that developing solutions, wideband solutions, can be very. I mean, at least you highlighted, Rafael, that if you develop high band solutions, it can be very tricky in terms of cooling systems, in terms of power consumption, and also Pratim mentioned that they're working towards 200 nanometer amplifiers, which is I believe that these amplifiers should consume a lot of power, right? So is there any study on how to provide a very large bandwidth, but at the same time you can optimize the power consumption? Is it something that you guys can comment on?
I don't know if I can go first.
Yeah, go
Yeah.
first. Feel free.
Yeah, okay. I think for us, I think what paves us for really the optimization of power consumption. This setup that I showed was based on discrete components. So of course, then you need all the devices are robust, so you need more power than that. But what paves way to really to reduce the power consumptions is photonic integration. So as we go smaller, we can have less power consumption in these devices, and also, yeah, and also the footprint is also important. So you don't need not just power, but also don't need big cases, big racks, and everything to support these devices.
Yeah, from my point, yeah, I completely agree with Rafal. So, like when you speak of amplifier things, so mostly it is like a banks of diodes, some laser diodes, and then you have passives. So the power consumption is mainly from the diode side. Now, when you use like multiple pumps, you need separate power for each and every connection ports. So in this like photonic integrated system into a complete SoC, it will definitely reduce to quite an extent. And yeah, and also yeah, it's a very bulky system. It will be in terms of like speaking of suppose amplifier, you can't send all O to L band signal, put one amplifier and just amplify it. Like even if for doped also it's similar. So you need to separate, you need to each and every amplifier will amplify only certain bandwidth. You combine again, you transmit. So this is quite a bit of bulky setups. But from that point of view, Raman is good is like you don't need separate every band. Like we can separate in one stage and you amplify the entire spectrum because Raman will take in any region of the optical spectrum. It's an inherent. So you can reduce quite a bit of space in terms of using Raman. And in terms of power optimization, obviously, with the developing technology, currently what we are using are not commercial pumps or something, they are customized. So when this will be integrated into an SOCN system, it will definitely reduce down to an extent. Yeah.
Okay, so thank you, Prateen and Rafael and Elliot for answering those questions. Now we move to the last two talks. The next one is from Bruno. And it is entitled Input Power Choice for Wideband Scenarios and its Impact on Quality of Transmission.
Okay, thanks, Mateus, for the invitation. So, as Mateus already said, my name is Bruno Correa, and I'm a PhD student at Politecnico di Torino. And today I will present my research results called an input power choice for wideband scenarios and its impact on quality of transmission. So a brief introduction already spoke by several persons here that the wideband transmission can be a viable solution to increase the network throughput. It aims the transmission over the entire low-loss fiber bandwidth, which is around 50 terahertz for standard single-mode fiber. And this is a quick illustration and in an optical network and the optical line systems inside of it. And the case is that each amplifier it's target for a certain portion of the spectrum, and our work is focused on how we can improve the capacity in the OLS inside the optical network. So just a quick considerations about the wideband scenario, that in which scenario we must take into consideration the frequency variations of loss, chromatic dispersion and nonlinear coefficients. We also take into consideration the stimulating Raman scattering and its interaction with the nonlinearity generation. And the SRS effect basically will result in a power transfer from the high frequency channels to the lower frequency channels. So in a wideband scenario, we should take that into consideration, and it's how can I say, it's kind of, we need to take care in order to one band don't degrade too much the other band when they are being transmitted together. So yeah, the application of input power control in order to counteract the effects raised by the SRS, and focus on maximize the quality of transmission levels within an optical line system. So this is a quick example on how a wideband transmission and how the power is important in a wideband transmission. So in this case, we use the generalized signal to noise ratio, already spoke by Elliot. And this, we can see the quality of transmission for 3 scenarios in the C and L and S band transmitting only a single band. So especially the blue line, which is our main metric in order to evaluate the quality of transmission. And we can see that when we start to transmit C plus L band, we have a small degradation on the C band due to the power transfer raised by the SRS effect. If we transmit in a C plus L plus S scenario, we can see that we have a huge degradation on the S band, also because of the same effect. And we have also a degradation on the L band because it's receiving more power due to the transfer, and it is starting to enter in the nonlinear regime. So this scenario used the powers for the scenarios with a single band transmission. So we need to optimize this power in order to maximize the quality of transmission and, of course, the capacity in the optical line system. And here is a quick illustration of the methodology used. So here we can see that we have the optimum flat power for each band. And the power control unit, we take care of regarding to set up the working points for the amplifiers and define the power for each band. So we can have kind of a shift, positive or negative of this power, and apply a tilt of the amplifier for all the bands. So in this way, we can counteract the effects of the SRS. In our research, we made use of GNPY as quality of transmission estimator. And until now, we have compared 2 approaches, which is a brute force, exhaustive search approach, and we made use of the genetic algorithm in order to find the work points for these amplifiers. So here is a quick example in how the choice of power can impact the throughput of an optical line system that we showed here. Total number of light paths per bit rate of 2, 3, and 400 gig for 3 types of OLS with 5, 10, and 15 spans. And we see that if we remain with the flat power, we have we have a worse performance compare with the both approach that we use. We also can see that the genetic algorithm was able to slightly increase the number of light paths with higher bit rate, and it was able to find this throughput with around 75% less tries. So quickly, a brief conclusion. To define and control the launch power for its spectral band is fundamental to counteract the degradation raised in the wideband system, mainly because of the SRS effect. And smarter ways to control the amplifier's working point can increase the optical line system and consequently the optical network capacity and enable the usage of a wider spectrum. So thank you again for the invitation, and any questions you can drop on chat or you can send an email. Thank you.
Thank you very much, Bruno. And now we move to just a reminder, if you have questions for Bruno, you can put in the chat, or and then we can discuss it later on the last Q&A session. So we move on to the last talk, which is from André de Souza from Itinerário Portugal. And the presentation is entitled Efficient Estimation of the Quality of Transmission and its Application.
Hi, Matheus. Thank you
Hi,
for
Andre.
the introduction, and thank you for organizing this event. The presentations are really good.
Nice.
So now I'm sharing my screen. I guess you're seeing the
Yeah,
presentation.
very clear.
Yeah. Okay. So I'm Andre. I'm represent a partnership between Infinera and Técnico Lisboa here in Portugal within the one project. I'm going to talk to you about the efficient estimation of the quality of transmission and its applications. I'm going to keep this presentation short, so I'm going just to indicate the main problems I'm searching on. And if you have any questions about the results I'm getting, you can send me an email or ask some questions after the presentation. So everyone already talked about the motivation of going to wideband, so I'm not going to repeat it. I'm just going to go directly on the questions. First, I'm going to talk to you about the efficient quality of transmission, the need, the interest of having an efficient estimation. So forecasting the quality of transmission of a light path is crucial for the design and management of optical networks. Suppose that you are a manufacturer of optical devices for optical networks, and then an internet network operator contacts you and says he wants to buy your equipment, but he wants an estimation of the capacity and the cost. For example, for a network like this one I'm showing, the Italian national network. And okay, so you want to get a result that is better than your rivals, than the other manufacturers. So you run optimization multiple times to get the best results you can get. And this network has 42 nodes and 71 connections. So you have to optimize the power, as Bruno showed, for every connection and multiple times with multiple variables, and it can take some time. And as Elliot said, the models are more complex for a wideband scenario. So it's really important to develop or to find fast and accurate quality of transmission estimation algorithms. And that's one problem I've been working on. So analyzing how much you can simplify the models and still get a good estimation of the capacity of your system and to get a faster optimization. The next problem will be which bands to use. So you get as everyone said, you get a large option of bands to use within the low loss window of the current fibers. Mainly we'll be using just the C and L solutions commercially, and the technology that enable other bands are still under development. So I expect the next step to be the S band, because it still have a lower loss than the E and the O band and has still a high chromatic dispersion. But how to know if the S band or any other bands will be efficient to deploy in a techno-economic criteria? So the QoT estimator may be used to predict the capacity benefits of these fibers, supposing that the characteristics of the technologies are mature enough, like are close to the technologies that are being used in the CNL bands. Okay, so just to conclude this very short presentation, I talked about two main points. The first one is that the development of fast and accurate quality of transmission estimation algorithms is essential, and that these quick KOT estimators may be used to predict the capacity benefits of multibands, even though the necessary technology is still in development. So that's it. Thank you. If you have any questions, just send me an email or put on a chat. Okay.
Okay, thank you very much, Andrea. I'll just wrap up with the very short Q&A session here. Just share with you. So is there any question from the audience? So far, I haven't seen any, but I have two questions. Actually, it's a question that you guys also can discuss together because it has a lot of synergy with what you have presented. So, Andrea, you mentioned, for example, that you want fast QoT estimation methods, and Bruno mentioned that he used, for example, genetic algorithm to optimize the power distribution. In terms of time, for both of you, what is a fast QoT estimation method and what is a fast optimization method for the power distribution? Did you guys already, Bruno, did you ever investigate any other optimization method that can be faster? Because these meta heuristics, they usually take some time to optimize, and we're talking about network-wide scenarios. You don't want something that takes too much time, right? And for you, Andrea, I don't know, you have considered, for example, using channel models that have like closed formulas or channel models that use these integration formulas and so on. So that's something you guys can work out now.
Okay, I can start, right, Andrea? Okay, yes, it's kind of is expected from the operator perspective that these optimizations run in a reasonable time, kind of a few minutes. And yeah, especially for wideband scenario, we still weren't able, let's say, to achieve that scenario, let's say the best scenario possible for the operator to run with. But yeah, the main point is that it's really tricky in a wideband scenario, especially if you do kind of a pay as you grow approach. Because the point is that you can define in a reasonable time, set up the network, everything working out, and after a while, your operator decide to increase, let's say, to go for another band. So this aspect is a little complicated, but yeah, let's say with this smarter way meta risk, we already were able to reduce the computational time. Let's say today for the C-band, as we don't have too many parameters, we just do a power sweep and find the optimal power. This won't be practical anymore in a wideband scenario. So besides the fact of the optimization itself, the optimization can run with which let's say which different types of modeling. So if beside the optimization, we also have, this is Andrea can talk a little bit more about it, but if you also progress in a way in modeling in a faster way, I think combining both of things, it's let's say a practical solution for the network operators.
Yeah, I would like to add just to what Bruno said, that these meta-heuristic algorithms are also good for multi-objective problems like the ones we have. So you can select in the Pareto region the best solution, the solution that suits more your needs. So it's good to use meta-heuristic algorithms for this. And about the models, yeah, as you said, I think you already know something about these models, like the closed form ones, the integration. And yes, as Elliot said, we don't have a lot of experiments to compare with the models we have on the S band, for example, and even if you go to the E or to the O band. And I'm considering that the GGN, the one that uses integrals and doesn't make a lot of simplifications, is the most accurate one.
Mm-hmm.
And I'm also comparing the performance of closed form ones, because the closed form ones are much faster. And but of course, to get a closed form expression, you have to do some simplifications that actually lead to some inaccuracies in real applications. So, and this, depending on the amount of inaccuracies, you have to work with a bigger margin when you are optimizing your network, planning your network. And a lot of works have already shown that having a lower margin is better. You have a more efficient use of your network. So yeah, the work is like seeing the trade-off between accuracy and time, optimization time, and then the final capacity of your network, the final efficiency of your network.
Okay, so thank you very much for answering the questions. There is one more question actually in the chat. I would kindly ask you to enter it in the chat because we are running out of time. Sorry, Geronimo. It's a very nice question, but I think we need to wrap it up soon. But you guys can chat it in the can answer it in the chat. So to wrap up the event, I would like to say thanks to everyone, especially say thanks to the ESRs who have accepted the challenge of showing. It's very difficult, the challenge of putting in non-scientific words what you're doing, especially when you're talking about a very high-tech area, very high-tech topic. But I would like to say thanks for the effort. Were really nice presentations. Unfortunately, not all the ESRs, because we're 14, could present their works here, but we're really happy to have some of you guys giving like a very broad view of what we are doing in the one project. I'd like to say if you have questions about the one project, if you are interested about it, just check this link here. You can see more, learn more information, learn more about us in this link here. And I would also like to say thanks to Tatiana, who's the project manager of our one project, and Elzen, who is our internal team assistant, on providing some help in organizing this event. So I'd like to say thank you once more, and I would just like for one more minute to take a picture with you all presenters. If you can turn on your camera, maybe we can. Yeah, we can take a picture, screenshot of everyone. Second, still waiting for some of you guys. Weird on my computer here. I have two computers on. One of them, I can see everyone. The other one, I cannot see, but okay, I'll just 1 second. Let me see if it looks good now. 1 more second. No, it didn't work, so it's more. Now it worked. Yeah. So, yeah. So thank you guys once more, and you have any final words to say something? Of course, we could not show everything about the one project, but at least I think people in the audience could have like a very light taste of what we are doing in the project. Any final words from you guys? Any comments? No? So, okay.
All good.
What?
All good.
Okay, awesome.
Really nice event, Matheus.
Yeah, nice. It was a nice event. Congrats, Matheus.
Thank you all for your contributions. Okay, so we see each other maybe next year. If someone wants to follow up with it, it would be really nice. So I think we can wrap up the meeting now, and have a nice day, everyone.
Have a nice day.
Bye.
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 Bye.